Now that we're familiar with the periodic table a little bit, then it's time for us to start talking about the structure of atoms in a little more detail. And now this is one of the first pieces of vocabulary that we're going to get this chapter, and that is isotopes. Isotopes are different versions of an atom of the same kind of element. And what's different is by the number of neutrons. So hopefully what you've understood so far is that an element is defined by its atomic number, its number of protons. So elements all have to have the same atomic number, and a neutral atom has the same number of protons and electrons, because the positive charge of the protons is equal to the negative charge on the electrons, and so in order to have no net charge, they're going to have the same number of protons and electrons. And there's a variable number of neutrons. And most atoms have more neutrons than protons. This isn't 100% true. There are some small atoms that have the same number of neutrons and protons, and there are some atoms that have fewer neutrons than protons, but usually not by very much. So when we look at isotopes, we have a complete isotope notation. And the complete isotope notation is the elemental symbol, the atomic number is down on the bottom left, and the atomic number we use the capital Z just as a reminder, and then up here we have the mass number, which uses the capital A, which is the number of protons plus the number of neutrons. So that's our complete isotope information. And when you look at the box on a periodic table entry, the elemental symbol is usually in the middle, the atomic number is usually above it, and then there's some kind of number down here that's not exactly the same as the mass number, but sometimes it's pretty close. And this is the atomic weight, or the atomic mass. And it's really the average atomic mass of the element. Now I showed you the mass of the proton and the neutron in kilograms, but we also use a unit called the atomic mass unit. And one proton has a mass that's almost the same as one atomic mass unit. It's 1.00728 atomic mass units. And sometimes you'll also see Dalton. And these are all the same thing. One neutron is slightly heavier. It has a mass of 1.00867 atomic mass units, or Dalton. And the Dalton has an abbreviation DA. I actually won't use the Dalton basically ever, but we're going to see it on web elements, and I wanted you to know what these are. Okay, so the mass of a proton is about 1 atomic mass unit, and the mass of a neutron is about 1 atomic mass unit. So when we look at an element like carbon, let's switch over to web elements here for just a second. Notice that on carbon, the mass that's underneath the carbon is 12.011. So if we think about the carbon, We already noticed that carbon has two isotopes. Carbon has carbon 12 and carbon 13. Both of them have an atomic number of 6. And if we have carbon 12, the mass number tells us that we have 6 neutrons, because 6 plus 6 is 12, so 6 protons and 6 electrons. And this mass number tells us that we have 1 extra neutron here, but we still have 6 protons and 6 electrons. So if the mass of each of these neutrons and protons is about 1 atomic mass unit, and electrons are about 1,000 times lighter, and so they're going to have mass that comes out here in the thousandths place, right? They're only going to affect this probably third decimal place out in terms of their mass, unless there's really a ton of them, and then maybe they'll be out here in the hundredths place. But anyway, they're not going to affect the whole number part of the mass. So when we go back over to Webb Elements and we look at that mass, we can see that carbon, which has 6 protons, has an average atomic mass of a little over 12 atomic mass units, which makes pretty good sense if most of our carbon is carbon 12 that has 6 protons and 6 neutrons that each weigh about 6 atomic mass units. Okay, so this seems pretty good. But now let's look over here at chlorine. We have chlorine 37, and its average atomic mass is about 35. So let's take a look at what our isotopes are. The isotopes for chlorine, I should back up here and say, Webb Elements is a great place to find isotope information, and I hope that you make use of it. There's lots of information on this website. I usually skip straight down. You've got the chlorine name symbol right here, atomic number, so that's the number of protons, and then we have a bunch of different information. But let's zoom on down basically to the bottom where it talks about isotopes. We want to click on this More Isotopes and NMR Data. And I should delete this. Okay, so what they tell you first is the naturally occurring isotopes. So let's look. We have 2 isotopes for chlorine, chlorine 35 and chlorine 37. But what's different here between the carbon 12 and 13 is that unlike carbon 12 and 13, carbon 13 is very scarce. There isn't very much of it. But let's look over here. Chlorine 35 is about 76% of all the chlorine atoms that you will find. That's what this natural abundance means. And the chlorine 37 is about 24%. So that means 1 out of every 4 chlorine atoms that's hanging around in nature is probably a chlorine 37. And the other 3 are probably chlorine 35s. That means chlorine 37 and chlorine 35 both make a pretty significant contribution to the overall average atomic mass. But rather than just averaging the mass, like normally in math when we do an average, we add up all of the numbers that we have to consider and then we divide them by the total number that we have, right? Here, we only have 2 isotopes, so we can't just add the masses up and add them by 2 because 75.78% of them are going to be chlorine 35 and 24.22% of them are chlorine 37. So instead of doing a instead of doing a regular average, we're going to do what's called a weighted average. And we're going to multiply the mass by the decimal form of the percentage. So let's see that happening. Okay, chlorine 35 has a mass of 34.968852721. And then the 2 numbers that remain, these are uncertain digits. And the units are atomic mass units. And this was 75.784%. This is our first uncertain digit. So notice that our mass has a lot of significant digits. The mass of an atom is generally known very well. The percent abundance is known a little bit less well because in actuality it varies depending on where you are in the world. So we can't have quite as many significant digits with the percent abundance as we have with the mass. But the mass of an individual chlorine-35 atom is known very well. So let's look at that chlorine-37 atom now. Its mass is 36.9659026211 atomic mass units, and its abundance was 24.224%. So if we want to calculate the weighted average, then we're going to take the percent abundance and convert it into a decimal form. So we take this number, divide by 100. And I'm going to include that first uncertain digit because it is one of our significant digits. Now, when I write down the atomic mass unit, I'm going to be a tiny bit lazy because I have a lot of decimal places here, right? And there's more significant digits here than there are here. So I know that I'm not going to keep all of these in my final answer, so I'm not going to bother with the uncertain digits in the masses. So I'm going to take this and I'm going to multiply the weighted, or excuse me, the weighting here, the percent abundance in decimal form, which we might call the fractional abundance, times the atomic mass. And then I'm going to do the same thing with the other one. And I'm going to add these together. So I will go ahead and show my work. When I calculate these, I get 26.501 atomic mass units with 5 significant digits from this number right here. And then I get 8.9546 atomic mass units from the second mass using 5 significant digits from the percent abundance. And I add these together, and now I have addition rules, so I need to look and keep the smallest number of decimal places, which is going to be 3. So when I add these together, I'm going to get 35.455 atomic mass units, which matches up really well with what we see on the periodic table for chlorine. Right there, 35.45. We sometimes end up with slight differences in our last decimal place, just depending on how often the periodic table has been updated, because sometimes the masses get updated more. I mean, the individual isotope masses get updated a little faster than the periodic table. Okay, so that's the weighted average. Let's try another one. Let's look at silver. Silver has elemental symbol Ag, which you should start learning. So go ahead and pause the video, go over to Web Elements, click on it and find the isotope information, and try calculating the percent abundance. Okay, hopefully you took time to go and find the isotope information. You should have found that there were 2 isotopes, silver 107 and silver 109. And I should note that there are other isotopes, but they're radioactive, and typically their half-life is small enough that they don't contribute to the overall average atomic mass in a significant way. So when we do our calculation for silver 107 and 109, these actually almost have a 50-50% abundance. So we have for the first one 0.518397 times 106.9051 0.092 atomic mass units, and 0.481617 times 108.904756 atomic mass units. And when we multiply these each individually, we should get 55.4193 atomic mass units and 52.4504 atomic mass units for the two weightings. We add those together and get 107.8697 atomic mass units. Now notice that this has more significant digits than what is being retained on the periodic table for silver right here. And often the number of significant digits that are displayed on the periodic table are just limited by space. So on Web Elements, you know, this is already a fairly small font on my masses, and if we were to display more digits, that would have to be even a smaller font. So keep in mind that the significant digits that are shown are not always the maximum that are available. So if I had a mass of silver and I wanted to do a calculation with it that involved the molecular weight, and I had more than 5 significant digits, I could go and calculate the average molecular weight to more significant digits, or I could look it up in another location and get more significant digits. And that's always a good plan. If you have more significant digits than the standard value that you're using, go and see if you can find one in the standard value that will give you more significant digits so you don't have to round from your careful measurement. Okay, so if you want a little bit more practice with two isotope masses, you can practice with bromine, antimony, or indium. These all each have two isotopes that are naturally occurring. So you can practice doing those and then compare the mass that you get with what's on the periodic table, because that will tell you if you get the right answer. So before we move on, I actually wanted to show you how we deal with more than two naturally occurring isotopes. So let's look at silicon, which has the elemental symbol of Si. And this has three naturally occurring isotopes. They are silicon-28, silicon-29, and silicon-30. And we're going to deal with calculating the average atomic mass exactly the same way that we did for 2. So if you're feeling enthusiastic and daring, pause the video here, look up the numbers on Web Elements, and see if you can calculate the average atomic mass before I do. Okay, hopefully you went ahead and took that opportunity. So when we look at silicon-28, we find that it's the most abundant isotope. It's 92.22977% abundant, so that's 0.922, etc. And its mass is 27.9769271 atomic mass units. Now, the silicon-29 is only 4.68%, and so remember when we turn that into a decimal, it's a 0.4683225 multiplied by 28.9764,949. The same is true for silicon-30. It's about 3%, so that would be 0.0308725 multiplied by 29.9737707 atomic mass units. Hopefully I didn't make any typos in here when I was copying numbers from Web Elements, but please let me know if I did make any math errors. 25.80306 is what we get from our first number. That's a lot of significant digits. I had to count them up. That's 7. And then our second number is 1.35704 atomic mass units. and the third is 0.925365 atomic mass units. And now we're on to addition rules. And so we're going to keep 5 decimal places in our final number, which should be 28.08547 atomic mass units. Okay, so hopefully you are feeling comfortable now with calculating the average atomic mass from the isotopic abundance. This is how it is done. Now you also know if you have other things that you need to do a weighted average for, you know how to do it. So let's go ahead and review practicing some isotope notation as well, circling back to the beginning of our video. Because one of the things that you can get from isotope notation, you can also figure out which element you have. So here's how we're going to practice. Go ahead and find the element with atomic number 53. What is it? And then what is one of its isotopes? And I'd like you to write the complete isotope notation. So pause the video and go track that down. Okay, hopefully you found that element number 53 is iodine, and it only has one isotope, which is isotope 127. This is another way of writing an isotope notation. It's not the complete isotope, it's just the elemental symbol with a dash and then the mass number. So the complete isotope notation for this isotope would be I-127-53. Okay, so let's go ahead and calculate, and find the complete isotope notation. Here's another practice problem. I should say instead, write the complete isotope notation. For an element that has 38 protons and 46 neutrons. So pause the video and go figure out which element that is, and then write the isotope notation for it. Okay. So first, hopefully you went to look and see which element was atomic number 38, and you should have figured out that that was strontium, Sr. And so we already can put the atomic number down here. So we have the atomic number. Now we need to calculate the mass number. We have the protons and the neutrons though, so we can just add those two numbers together to get the mass number, which would be 84. Let's practice a couple more. Write the complete isotope notation. For elements with 11 protons and 12 neutrons, and 18 protons and 18 neutrons. Pause the video and go track those down. All right, I bet you're getting fast at these now. So 11 protons gives us sodium. with an atomic number of 11. And then 11 plus 12 gives us 23. So this is our most common isotope of sodium. 18 protons gets us argon. And then 18 plus 18 is 36. Okay. One more practice problem. Find the number of protons, neutrons, and electrons in the cadmium 110 isotope. Pause the video, go check that one out. Welcome back. So if you look at the periodic table, you can see that cadmium is element 48. So that means that it must have 48 protons and 48 electrons. And then 110 minus 48 is equal to 62. So that means that it has 62 neutrons as well. Hopefully you were feeling comfortable with working out both what the subatomic particles are on different isotopes and also calculating the average atomic mass based on isotopic abundance.